in South Florida in music education, so that's why I'm talking to you about astronomy. So we'll just jump right into it. So this is, well, I'll just go right straight from here. The women who created modern astronomy. You'll see this picture several more times later on in the presentation. So let's see, when I'm trying to get my other little picture out of the way, the little picture of me talking, which is, that's okay. Okay, first, uh, this presentation draws very heavily on two main sources. The first one that I saw was this article by John Dvorak in Sky and Telescope magazine, August of 2013, which was called The Women Who Created Modern Astronomy. So that's where I stole the title from. And then more recently, I read the book, The Glass Universe by Dava Sobel. And if you haven't read, if you're interested in this kind of stuff, if you haven't read any of her books, she's a space historian. And one of the things that is big for her is she likes to go to the original documents, especially correspondence and letters and things like that. So her first big book was Galileo's Daughter, which had a lot of basis of the letters written back and forth between Galileo and his daughter. Okay, and she's also done one longitude about the invention of a chronometer that would work on a ship and things like that. So, so basically, I'm just telling you where I stole all my material from. Okay, so back in the day, around 1800s, more or less, astronomy was just starting to go from simply mapping the sky, just going through and getting accurate positions for all of the stars, to being able to actually study individual stars. And so new techniques were being developed along the way. And so one of them was spectroscopy. Oh, I'm good, I said it right. I'll probably not try it again. And so spectrum. Okay, you get a prism, you put the sun, shine the sun through a prism, and you get a spectrum. You get the rainbow. But if you have a more detailed, if you can magnify on that rainbow, this is a picture of the sun spectrum. You'll see in the sun spectrum these dark lines where certain colors and very specific colors are not getting through. Okay, and so Fraunhofer, sorry, he's the one that invented the modern spectroscope, and to be able to see these lines, and he started classifying them just kind of basically. Now this is a more modern slide, and it says that lines are due to cooler gases in the outer layers of the sun, which at that time they didn't know. Okay, so Fraunhofer put a spectroscope on the sun, saw these dark lines, wondered what they might be, and this was in 1814. Now, he also aimed his spectroscope at other stars, bright stars that were bright enough that you could see the spectral lines, and notice they had dark lines, but they weren't all the same. They were in different arrangements. Now, it took, in 1859, Gustav Kirchhoff and Robert Bunsen of the burner fame were the ones that determined that these lines were made by specific atoms. If you heated up specific atoms, they would glow in the color of one of these lines. Or for certain cases, you could have a glass-filled container of the gas and shine a continuous spectrum, just a regular light through it, and you would get these dark lines. And so it was Bunsen and Kirchhoff that figured out what they were. And so now we know that, like, this D line here is sodium, and hydrogen is up here, and things like that. Okay, so that was the first chance to determine what was in the atmosphere of the sun. You have the surface of the sun, the photosphere, putting out the light, and then you have gases above it that are absorbing these certain wavelengths. And so this was the first chance to actually know what the sun was made of. Okay, so that was all very exciting. Move on to Angelo Secchi. He was a Catholic priest, an astronomer in Italy, and he was the head of what was then called the Roman College Observatory for 28 years. And so he went about to actually classify these different spectra of the different stars as they started collecting these different recordings of this star has this set of lines, that has that set of lines, etc. And so he came up with 5 classes. Okay, so class 1 was white and blue stars with broad, heavy lines, you know, the heavy hydrogen lines. Those are the ones in the blue end, like Vega and Altair. He had a subclass called Orion subtype, because these were a lot of the stars in the constellation Orion that had the same kind of lines, but they were narrow. And nobody quite knew what that meant. Class 2 was yellow stars like the sun, and Arcturus, Capella, things like that. 3 are the orange stars like Betelgeuse and Antares. 4 was carbon stars, and that's a whole separate group where there's just a lot of carbon in the atmosphere of those stars. Makes the star itself very, very red and had its own set of lines. And then you had a 5th class of emission line stars like Gamma Cassiopeia, where besides those dark lines, there were some things, some of those atoms were being excited enough that they actually glowed. And so you had dark lines and a few bright lines where the colors were actually brighter. Now, one thing to point out is that in this day, 1866, astronomy was still strictly a visual kind of thing. People are peering through eyepieces, and then they would draw for these spectral kind of things. They would draw the spectral lines, and they probably had a little template to put it on there. Okay, but so now the spectroscope was the one innovation in studying the stars. The next one was photography. Enter Henry Draper. He was the first one to take a photograph of the spectrum of a star. I think a few other people had already done the sun, but he got good enough equipment to take the spectrum of individual stars. And Draper quickly thought of the idea of photographs are much better because they're relatively permanent, and it's an objective record. You're not just relying on somebody accurately drawing these things on a template. And so you had a photograph, and it wasn't, I mean, it's open to interpretation, but somebody else can come along and see if they agree with your interpretation. And so that was an important thing. Another thing, that this is not something that Draper himself did, but that utilized, is this is the front end of the telescope here. Okay, and instead of having a spectroscope, the prism on the back end by the eyepiece, where you can look at one star at a time, he put the prism on the front part of the telescope, so that you could take a picture and all of the stars would be showing a spectrum. And you're going to see an example of that a few slides away from here. And so that way you could gather a lot more information. And I didn't really mean to click that, but that's okay. So besides Draper, Edward Pickering, who became the director of Harvard College Observatory in 1877, he quickly got the idea, or at least agreed with Draper, or however you want to say it, that having photographs of star spectra was a good thing, and would be good for studying the stars, analyzing the individual stars, etc. Now, he started at Harvard College Observatory, and in 1877, when you said the word computer, you were talking about somebody that was good with math. And so all of these astronomy departments and other things that had to do calculations, they had a collection of computers, of people that just sat in the room and analyzed the data and did the calculations, that kind of thing, and turned them over to the other people who would then help to interpret that. But their job was just kind of like the computer on your desk, is just to, shut up and calculate kind of a thing, basically. Now, these were mostly, graduate students, which in those days were mostly men. When Pickering got to Harvard, there were some women that were working as computers. Okay, well, Pickering kind of changed that. And here are the Harvard computers. This is about 1890. Okay. Now, one thing I need to point out about this picture is that they didn't always work all scrunched up like this. Um, they were all crowded into one end of the room so that they could get a picture for a photo op. And so you have our buddy, there's my cursor. So we have Edward Pickering here. And then while I'm here, I'm going to point out three of the women in here that I'm going to be talking in more detail later. You have Wilhelmina Fleming, Antonia Mare, and Annie Jump Cannon. And I'll talk about them in more detail as we get down a little farther along. So this is the Harvard computers. Now, sadly, in these days, they had another name, Pickering's harem. The other astronomers used to make fun of him because he had this whole collection of women. Okay, and well, he didn't care. He didn't care that that they were making fun of him because he decided that the women were better at the work. They worked steady, they were meticulous, they were accurate in what can be like mind-numbing work because you're just working at this stuff and you have to be able to stay focused and it has to be accurate, it has to be right. And this was the beginning of the age of cataloging the individual stars in the sky. Now, I have a story about, well, I'll go ahead and say it now. I always change my mind where I put this. Wilhelmina Fleming, okay? She arrived, no, I lied. When I get this individual picture, I'll talk about her then, okay? Now, let me go to a quote from The Glass Universe by Davis Sobel. That is a point that really needs to be made. When female computers of the Harvard College Observatory come up in present-day conversation, they are often portrayed as underpaid, undervalued victories of a factory system. And Pickering stands accused of giving them scut work that no man would stoop to do. Yet this is far from true. Before astronomy morphed into astrophysics around the turn of the 20th century, both men and the few women engaged in science were willing slaves to routine. This calculating, shut up and calculate. It was mind-numbing kind of thing, but this is how the things had to work. Pickering quickly decided that this collection of women did better work than the men when he first got there. And he paid them as best he could. And I'll get to that in a little bit too. Okay, so here we are in the Harvard computers. Let me talk about how they work a little bit here. So we'll take Annie Jump Cannon here. Okay, the photographs, there was like 6 men that took those photographs of all these star spectra each night, each clear night. And then they developed these plates and then the computers would then analyze them the next day. Now it was a photographic emulsion on a glass plate. And so the photograph, was put in a frame like this. There's a mirror down here to reflect light up into it. And then the one person, in this case, Annie Jump Cannon, would use a magnifying glass to look at the photographs and start classifying. So that she didn't have to take her eye off of what she's doing because she's classifying, she's recording exactly where on the photograph each of these spectra are, whatever. And those kind of things. And so she had each person at the magnifying glass had a recorder. And so they worked in pairs like that. Many of these recorders, there's not a whole lot of things written about them. But anyway, and so that was their job all day. Now, let me show you what they were looking at. Each one of these streaks is a star. So there's a star there. And then the streak is the spectrum. Okay, this is a negative image, and so those dark lines should show up as little gaps in the spectrum, but you can't see that until you get a magnifying glass going. Okay, and so each of these plates could hold hundreds, if not 1,000 stars, and they were in there classifying each one of these stars and then going on to the next plate. Now, next development is in 1882, Henry Draper dies. So his wife, Annie, who worked alongside her husband and was an accomplished astronomer in her own right, she was well off previously from marrying Henry from a sizable inheritance. And so she set up the Henry Draper Memorial Fund to bankroll Harvard College to their project to get high quality spectra of all of the stars in the sky. Not just the important, all of them, and publish a catalog of their spectral classifications. So the first edition had, where'd my pointer go? Yeah, over 225,000 stars. Okay, so, and they just kept going. They took pictures every night. Eventually, they got telescopes in the southern hemisphere to get the part of the sky that could not be seen from Harvard, so that they could catalog the entire sky. And this was the project. And now Anna Draper also funded other things, which I'll talk about in just a little bit after I get past Wilhelmina Fleming. Okay. Now, here's what I was almost said about Ms. Fleming earlier. And that is, she was a Scottish immigrant at a time when Scottish immigrants were not considered, didn't have a whole lot of high esteem in the country. Okay. She came to the United States with her husband because of her husband's business. It's not clear what he did. But along the way, she turned up pregnant and the husband bailed. He went back to Scotland, but left her here. And so she ended up just, to make a living, ended up being a maid in Pickering's household. Well, Pickering and his wife was pretty sharp too. Not much is written about her, but noticed pretty quickly that Miss Fleming was an intelligent woman and a sharp woman. And the story cannot be corroborated. Can't prove that it happened, but the story is one of those, don't let the facts get in the way of a good story, is that when Pickering showed up at Harvard and some of the male computers, he would like yell at him, said like, "You call this good work? My Scottish maid can do better work than this." And so, well, he hired her and she did. So, yeah, he hired her to come in and do the computing. And if you remember from that other picture, Miss Fleming was kind of standing there. She quickly became the person in charge of the computers. And then the other thing, which comes along a little later, but I'll go ahead and say it now, is that, as I said, Pickering did his best to pay the women what he could get away with, but he had to go through the college board and he had to justify it. Well, they were taking photographs, they were getting cataloged, they were being stored, and so to be able to give Miss Fleming a raise, and she was already doing this work, he made up a position, the curator of astronomical photographs. And so she was not only in charge of the computers, but she was in charge of classifying, cataloging, and storing all of those photographs that were being generated, several a night, tens of maybe 20 a night, kind of a thing. Okay, so Pickering asked her to classify all these spectra in Secchi's scheme, those 5 letters, 5 numbers that Secchi had. Well, by this time, spectroscopes were getting better. And she realized she was seeing more detail than what Secchi's scheme could deal with. The Secchi scheme was too simplistic. There were fine graduations within class 1, class 2, etc. She thought she could do better. She told Pickering as such, and he said, have at it. And so here's Miss Fleming's original classification. 14 classes, lettered A through O, leaving out J because J in German can be easily confused with I. And a little side note there, German then and now is still considered very much an engineering kind of language. I have an electrical engineer friend that, he had to have a foreign language for whichever degree he was doing there. And so he took German for reading because, you may not necessarily need to be able to speak it, but you should be able to read the German journals. Okay. So he came up with this classification. Second scheme, class one, um, was covered A through D. So, individual differentiations between A, B, C, and D. Okay, and then two covered E and L, E through L. Three was M, four was N, and five was O. Okay, so after coming up with the scheme, Pickering published a scientific paper. And he had his name at the top, but in the subtitle, he made it pretty blunt. I should have written it down. The phrasing was classification based on the measurement and analysis by Wilhelmina Fleming. Okay, so he gave her as much credit as she could, basically said she did all the work. But certainly in those days, if they published a paper with her name at the top, nobody would have paid any attention to it. Okay, our next woman, Antonia Maury. Now, she, first of all, was a little different because she had an astronomy degree. I don't think she was part of this part of it, but Annie Draper, if you remember her, she set up this fund for Harvard College Observatory. She also set up scholarship funds to help women get astronomy degrees and other science degrees. Okay, so Antonia had an astronomy degree from one of the women's colleges. They were still segregated colleges, but she wanted to get in and do this work. Well, Pickering was a little reluctant to hire her because she had a degree and he thought she should be doing something a little less routine than this computing kind of stuff. But she insisted she wanted to do the work. She wanted to get into the nuts and bolts of these spectra and what they mean. She came up with her own classification scheme. Okay, 22 classes, just numbered 1 through 22. But part of her scheme included also a subscript A, B, or C, because a 14C was only a little bit different than a 15A, that kind of thing, to try to make a more smooth transition from one to the other. Okay, well, as Miss Fleming just focused on classifying what she was seeing, Miss Maury really wanted to sort out the physics involved to make these different classes. Okay, the final classification scheme ends up, the final Harvard classification scheme that everybody uses a little bit of Maury's classification and a lot of Fleming's classification. Okay, and one of the reasons that Ms. Maury could come up with 22 cases is also the spectra were getting better. They were seeing more details. They could see a little bit more difference from one to the other. Now, our third woman we're going to talk about, Annie Jump Cannon, also a college graduate, who went very far in astronomy, which I'll talk about toward the end there. Okay, by the time she arrived at Harvard College Observatory, it had been determined that 99.3% of all the stars fell in just 6 classes, A, B, F, G, K, and M. And the more detailed, they were better and better spectra, the more detailed spectra showed that the others were redundant. It looked kind of like a difference in the worst, lesser quality spectra. When you had better quality, it's like, oh, this is the same as that. Okay. Now, when Miss Maury was working on it, she determined that B should come before A, based on a transition of those spectra. Okay. And then O was still, they didn't know what to do with the bright emission lines. Wasn't quite sure what was causing that. Okay, so Annie Jump Cannon, looking at the yet better spectra, saw that O and B stars had those Orion lines, those emission lines. And so, and then with knowing that they both had emission lines, so O should be up there by B, and actually decided that O should be at the beginning. And so what started off with a simple A through M classification scheme ended up being, oh, be a fine girl, kiss me. You know, and it's, which is the standard mnemonic that people use. I'm just such a nerd, I just memorize it. But anyway, and so, yeah, what started out is a simple looking alphabetical kind of thing came up into this kind of thing. Okay, now, also by the time we got to this final sequence, it became clear, it was becoming clear, it wasn't absolutely clear, that the differences between each of these spectral classes was primarily a result of the surface temperature of the star. And now I should point out that at this point in time, they didn't know how stars produce their heat. They're just, they did. And there was a lot of discussion about how that should work and how they should be so long-lived and et cetera. But yeah, they pretty much sorted out that this is a difference in temperature and surface temperature of, you know, of what's producing the light that then goes through these the outer atmosphere of the star to get to our spectroscopes. So here's our final result, and this is a very nice one here of a spectra. Now, one thing to talk about here is black body radiation. You know, it basically, for something that just a black body is something that it perfectly absorbs radiation and emits it, re-emits it, kind of a thing. And it's an idealized kind of thing. It's kind of the physicists assume the cow is a perfect sphere kind of a thing. But and so the hotter stars have a lot more blue. Notice that the hotter stars down here, there's hardly much red going on. Okay, whereas you get to the cooler stars, not much blue there, and a whole lot of red. Okay, and then also, so now you can see the thin hydrogen line for the O and B stars. But then when we get into the A stars, the lines are getting thicker. And then as we get down farther along, the hydrogen lines kind of get a little bit less, but then all these lines here, the sodium line that I mentioned in the sun spectrum, start showing up a lot better. And then as you get to these cooler stars, there's spectral lines all over heckin' creation. All right. And and I need to point out this little thing when you start talking about stars. The term metal. Okay. To an astronomer, if it ain't hydrogen or helium, it's metal. Because, well, I won't get into all that, but yeah. So when you hear an astronomer talking about a metal-rich star or a metal-poor star, they're talking about things that are not hydrogen and helium. Okay. But now, the thing it is, once they came up with this spectral classification that they could determine things along the lines of surface temperature of the star by the spectrum and what at least the atmosphere was made of. And it's just, you know, an assumption that if the atmosphere is made of that, it came from the star, and what the stars were made out of. This, ladies and gentlemen, boys and girls, children of all ages, launched modern astrophysics. This system allowed astronomers to begin to piece together exactly how stars lived and how they died. Now, it'll be another decade or so before they discover nuclear fusion and are able to determine how stars produce their energy. But this is the beginning of studying individual stars, the life and death of stars, the lifestyles of the rich and famous, and that kind of thing, as opposed to earlier astronomy, which was just simply, where are the stars and how bright are they? And so the work of these ladies launched modern astrophysics. But the women of Harvard College Observatory were not yet done. Enter Henrietta Leavitt, who came along after all this. Let's see, Annie Jump Cannon and Wilhelmina Fleming were still there, but they were kind of like winding up their careers at that point. Okay, so Henrietta Leavitt was another college graduate from a women's college. And so she was put on here, as I mentioned earlier, that the telescopes at Harvard College Observatory were all over the globe. And so they're photographing the entire sky. And basically when they got done with photographing all of the sky that they can see from that part, they started over and just kept doing this in a constant cycle. Well, this made it possible to track changes, stars getting brighter or dimmer, new stars, nova, supernova showing up, going away, things like this. Now, Miss Leavitt, in looking at, remember that photograph back there with the whole collection of spectra all over everywhere? Okay, Miss Leavitt came up with a way to relatively easily pick out variable stars in these plates. And if you track me down later somehow, if you want the gory details of how that worked. It's also the technique that Clyde Tombaugh used to discover Pluto. So, okay. And so she started getting really good at spotting variable stars and tracking their cycle of getting dimmer and brighter and dimmer. Brighter is this way and dimmer is that way, right? Okay. And so yeah, she became known around there as the variable fiend or something to that effect. And so Pickering wanted to use her skills, asked her to study variables in the small Magellanic Cloud. Now, the small Magellanic Cloud is, it can't be seen from this latitude, it can be seen from the southern hemisphere, or at least you have to at least get close to the equator. And we now know it's a satellite galaxy of our own galaxy. They didn't know that back then, but it was pretty obvious that it was a big cloud of stars, a big cluster-like kind of thing of stars. And so Pickering asked her to study the variables in the small Magellanic Cloud. Magellanic as in Magellan, the first guy European to go around the world. And in particular to study Cepheid variables. Now, Cepheids, a name for the first one that they found this pattern, Delta Cephei, they have a distinctive light curve. They rise up relatively quickly from dimmest to brightest and then tail off slower. And so I guess for you it'd be that way, wouldn't it? Okay. And so if you look at the light curve, you can tell that this is a Cepheid variable as opposed to, there's a couple others out there with slightly different curves to them. So she started studying the Cepheid variables and she found this relationship. So this is a chart. It's a kind of logarithmic. So for those of you that are really good with math, don't pick on me about that. And so this axis is brightness. And this axis is how long it took to go through a full cycle. Okay. And now you may notice that the brighter stars have lower numbers. That's the way astronomers figure magnitude. I'll explain that some other time if you really like it anyway. It was pretty much known, it was pretty much assumed that all of these stars were basically the same distance away. They might be in the front of the cloud, the back of the cloud, but they're all basically the same distance away. And Miss Leavitt spotted this trend that, okay, this top line is the maximum of particular stars, and this bottom line is the minimum. And you notice, first of all, the range from dimmer to brighter was about the same. Okay. And so this is the I forget which version of the best fit line. What's their best straight line that fits all of this data? Because there's going to be some scatter in the data because of dust in the way. One's a little bit farther on the back side of the cloud, one's in the front side of the cloud. But by studying this, she saw a clear trend that the dimmer stars also had the shortest period. And the brighter stars had the longest period in a relatively linear, kind of logarithmic, but still linear relationship. This, ladies and gentlemen, created what astronomers call a standard candle. Because you can look at a star as long as you can see that it's a Cepheid variable and that it's and that you can measure the brightest and the dimmest, then you know how bright it is, at least in relation to these guys in the Small Magellanic Cloud. And okay, if it's farther away, it's going to be overall dimmer, but you can work that relationship, and at the simplest, you can determine how much farther away that Cepheid variable is from the ones in the Small Magellanic Cloud. Okay, so that was a big, big deal. First thing that it did was, okay, they called this is the Andromeda Galaxy. Okay, they called them spiral nebula because telescopes were just now getting good enough to see individual stars in these galaxies. And so they just looked like spiral, oh, hi there. There's my line. You know, spiral clouds. And there was much debate as to what they were. You know, maybe this is a solar system in the process of forming. Didn't know how far away they were. All that kind of stuff. And so there was a great debate going on at this point in terms of, is all these stars, is there one big universe, one big galaxy, or is our galaxy part of a system and these other things out here, these other guys are galaxies in their own right, which some people even call them island universes to start off with. And so Edwin Hubble, coming along a little bit later with bigger and better telescopes, was finally able to spot, it was up around in this part of the galaxy, what he first thought was a nova, but he's found out it was a variable. And they studied it more, it was a Cepheid variable. And they were able to then look at the brightness of the variable in this galaxy, compare it to the Small Magellanic Cloud, and prove beyond the doubt that this was a separate star system outside of our own, because it was thousands of times farther away than the Small Magellanic Cloud. This was a big deal. Now, also using this, after that, and by the way, the Small Magellanic Cloud, where'd you go? There. You know, Andromeda Galaxy has its own little satellite galaxies like our Magellanic Clouds. So using the Cepheid variables, Hubble was also measuring what's called the redshift. And that is, as a galaxy or whatever, if it's going away from you, then the wavelengths get stretched out toward the red. And so that means all of those lines that you're looking at, you know, pretty much the continuous spectrum will look the same, but everything will be shifted one way or the other, whether the galaxy or whatever is coming toward you or going away from you. To use the analogies to make sure everybody understands, it's the same reason that when somebody is honking the horn as they go by you, the pitch goes down. You know, it's the same kind of Doppler effect that does that in light. And so with the combination of the Cepheid variables that could be measured in galaxies and the redshift, Hubble was able to pretty much, again, without any kind of real doubt, prove that the universe is expanding. And that was like mind-blowing to the community at that point. And so between the stellar classification and then Henrietta Leavitt's measurement of the Cepheid variables in the Magellanic Cloud, that is the basics for all of our modern astrophysics. That change, it was a Galileo seeing the moons of Jupiter kind of moment, where, okay, pretty much the Earth is not the center of the solar system, that kind of thing. You know, that Copernicus was right, that the sun should be at the center. And so all of those contributions from the women of the Harvard College Observatory set all of this in motion. And so that's why, you know, that article, and I agree with the title, these are the women that created modern astronomy. Okay, final couple of tidbits. Wilhelmina Fleming discovered the Horsehead Nebula. Those of you that are astronomers and know about the Horsehead Nebula. Now, she didn't see the Horsehead shape or anything like that. She's just studying this plate, sees this bright emission nebula, and made a note that there was a notch in it. Okay, it was other people that got better pictures that saw, oh, it looks like a horsey. But anyway, so that was one of the things. She didn't think it was any big deal. She just kind of marked it in there. Antonia Maury, now let me get a little aside about her. She kind of came and went from the Harvard College Observatory a few times. Going on to other observatories, doing other work, coming back to them. It was, as far as I can tell, was not an acrimonious kind of departure. It was just like, hey, I found a better job. Okay, go ahead, that kind of thing. But she also discovered the first spectroscopic binary. Okay, back to the redshift thing. The line is going to shift whether it's coming toward you or away from you. And she discovered stars that in a regular period, lines would look individual, and then they would split and then come back together. And that's because it's two stars orbiting around each other. And so at one point in the orbit, one's going toward you and the other one's going away from you. And so she was able to show that this must be two stars. We're looking at the combined spectrum of two stars, and they're orbiting around each other. Okay, so that was another big deal. Okay, now, come on, computer. There you go. Annie Jump Cannon got so good she could classify 3 stars a minute. Go back to your memory of that picture of all those, maybe up to 1,000 stars on a plate. And she was probably hard to keep up with by the person doing the writing down. And she's able to classify in about 20 seconds. This was this. This is an O. This is an O5. Okay. I forgot to mention that one on that chart there. Remember, Antonia Maury had 3 subdivisions. Well, when they got to the final thing, they went with her idea, but there's actually 9. So you have a G0 all the way up to a G9. Okay. Before you get to a K0, that kind of thing. But yeah, so the final stellar classification was mostly Miss Fleming's classification with several of the ideas that Miss Maury had in there too. Okay, so anyway, but yeah, Annie Jump Cannon, and then as it says there, she moved her way up. She eventually was appointed the William Cranch Bond Professor of Astronomy at Harvard. That's the top dog professor of astronomy at Harvard. Got a doctorate along the way, and she was in charge of that until her retirement, and was the first. Pretty sure she was the first female director of an observatory. Okay, and then last little tidbit: Henrietta Leavitt was almost nominated for a Nobel Prize in 1924. Probably the biggest reason that she couldn't be nominated was she was already dead. She died of stomach cancer. Edwin Hubble often said, I mean, he kind of went out of his way to say that Henrietta Leavitt deserved a Nobel Prize because her work allowed him to do his work to prove that galaxies, that there's a universe full of galaxies, not just one big universe that we're looking at, and that they were expanding. And so he gave her credit as much as he could to her work. And last little thing about both Pickering and his successor, Harlow Shapley, is that they did their best to make sure that the women got the credit they deserved. Miss Leavitt's paper on the relationship between period and luminosity and Cepheid variables, that was published with her name on it at Pickering's insistence. By this time, the Harvard College Observatory had enough of a reputation that, probably some people muttered about it, but they still like, well, it came from Harvard, it must be good. And similarly, Harlow Shapley did that as well. Continued to make sure that the women that did the work got the credit. And so they were as progressive as the society could allow at that time. Is about all I can say. We look at it from our modern viewpoint, and they were still paid less, but that's that was just kind of the way it was. You really couldn't convince a college board, a personnel board, to be able to pay women. Although I believe by the time Annie Jump Cannon became the William Cranch Bond professor, she was paid the same as her predecessor. Okay, so that are the women who created modern astronomy. Okay, I'm going to unshare this, and we have 4 minutes for questions. Ask me anything about music or astronomy. Okay, yeah, I've not been able to see all of your comments, but
Unmute audio. Sorry.
Good sound system you got there, Michael.
Give me a minute. Somebody else go.
All right. Well, anyway, and it looks like we have the people coming in for the next event. So hi, all of you. Okay. Well, if you don't have any questions,
I have a question.
Okay, go to it.
Oh God, it was the tip of my tongue. I'm sorry. I was like having trouble halfway through the things that had come in and out of the panel a few times. How many women does NASA have right now?
Oh, I don't know that number. It's probably about, I don't know, Jeff, you might have a little, is Jeff still with us? Yes. You might have a little better idea, but it's probably, pulling a number out of a bodily orifice, probably about 30 to 40%.
All right.
And how many of those women do you think will be destined to go on a space mission?
That for the astronaut training, they're working pretty hard at having parity, and so yeah, I think probably in the next decade or so, as long as we have a space program going on, it'll be pretty
big gift.
Half and half. All right. Well, I think we're kind of close enough to being out of time, and so need to turn my glasses back on. So
awesome presentation. We loved it.
I'm going to go ahead and stop recording.
All right, but thank you all.